And we're live, maybe. Let's figure it out. I might want some more lighting, just a screen. Um, yeah, okay. Um, Welcome everyone. This is a special video, not because there's going to be any special content, but the symbolic thing here is that we've crossed 100. I've crossed 100 daily videos consecutively, with no gap in between. Some of them were not uploaded to YouTube, so if you go and look at my channel, it might be a little bit less than 100. Some of them were like posted on other platforms. Um, but basically, yeah, it happened. I don't know how. I don't know the like. I don't know if there's like any special things that I need to say, but this is the 100th video that I've done in the past 100 days. Um, Kind of exciting. Also, like the end of like basically a daily challenge of like 100 videos, which means that once I'm done with advent of code, I might take a little bit time off of making these, and then come back and maybe do a little bit more um, high quality, less frequent amount of videos. Um, we'll see about that. Don't expect like the quality to jump like exponentially or something, but yeah. If be interested in like if you stick around, you might see and learn something new. And now that we've got like the formalities out the window, I've got a very sour beer with me, and I think we can try and solve day 13. Day 12, I just didn't have the capacity and time to solve, and I might do that over the weekend, but I'm making no promises. So cheers, and let's dive in. I would say I had like free a few 20 like about 20 minutes before the stream, and I already pre-read some of that, but we are going to read that again, and then we're gonna start almost fresh. So, point of incidence. With your help, the hot springs team located an appropriate spring which launches you neatly and precisely to the edge of Lava Island. There's just one problem: you don't see any lava. You do see a lot of ash and igneous rock. What's igneous? I'm not even sure. Solidified magma. Okay. There are even what look like gray mountains scattered around. After a while, you make your way to a nearby cluster of mountains, only to discover that the valley between them is completely full of large mirrors. Most of the mirrors seem to be aligned in a consistent way. Perhaps you should head in that direction. As you move through the Valley of Mirrors, you find that several of them have fallen from the large metal frames, keeping them in place. The mirrors are extremely flat and shiny, and many of them have fallen. Of the fallen mirrors have lodged in the ash at strange angles. Because the terrain is all one color, it's hard to tell where it's safe to walk and when you're about to run into a mirror. You note down the patterns of ash and rocks that you see um, as you walk your puzzle input. Perhaps by carefully analyzing these patterns, you can figure out where the mirrors are. For example, so we've got like a bunch of like rocks and ash. Um, yeah, rocks and ash, and we do need to find like the symmetry line basically. So to find the reflection in each pattern, you need to find a perfect reflection across either a horizontal line between two rows or across a vertical line between two columns. In the first pattern, the reflection is across the vertical line between two columns. Arrows on which two columns point at the line between what? Wait, what? in the first pattern, the reflection is across a vertical line between two columns. Arrows on each of the two columns point at the line between the columns. Interesting. So we've got this one. In this pattern, the line of reflection is a vertical line between column 5 and 6. Because the vertical line is not perfectly in the middle of the pattern, part of the pattern, column 1, has nowhere to reflect onto and can be ignored. Every column has a reflected column within the pattern and must match exactly. Column 2 matches column 9, column 3 matches column 8, 4 matches to 7, and 5 matches to 6. The second pattern reflects across a horizontal line instead. So we've got that, and yeah, this one matches on, between lines 4 and 5. This pattern reflects across the horizontal line between rows 4 and 5. Row 1 would reflect blah, blah, a hypothetical row 8. Since there's not any pattern, it doesn't need to match anything. The remaining rows match up. Okay, just summarize your pattern notes. Add up the number of columns to the left of each vertical line of reflection. To do that, also add 100 multiplied by the number of rows above each horizontal line of reflection. Wait, what? Okay, so we need to add up the number of columns to the left of each vertical line of reflection. So we've got the index of this reflection line, the symmetry line. And also, we need to find any number of, if we've got any rows that reflect, we also need to add that up multiplied by 100. In the above example, the first pattern's vertical line has 5 columns to its left, and the second pattern's horizontal line has 4 above it, for a total of 405. Find the line of reflection in each of the patterns in your notes. What number do you get after summarizing all your notes? So first of all, if we actually analyze this one, I think this one also has a line of reflection here between lines 3 and 4. Is that correct? So we got this vertical position, but there's not like these are also matching. So what gives? Or is that incorrect? It's incorrect. Because here, okay, so we don't have a horizontal a horizontal reflection here. Okay, and in this one, we only have a vertical reflection. Okay, so in each pattern, we might have a vertical or horizontal, or maybe both, I don't know. And we need to find all of them. Okay? So now that we've got that, let's dive into the small code that I've already written. Oh shit, the thumbnail is Rust, but it's going to be Python today. Sorry for misleading people. I'm too tired and too drunk to code in Rust today. So let's dive in. Should I change the thumbnail? Probably not. Whatever. You're gonna find out it's Python, and you're gonna be okay with that, apparently. So this is day 13. We've got the inputs already pasted in. I've split them up into the thing. Hopefully they are split up correctly. Let's actually assert that. Assert. Yeah, let's just do that for a minute really quickly. Okay, cool. So yeah, it didn't fail on like we split it correctly basically. Now that we've got that sorted out, I think yeah, 1, 2. Yeah, okay, so 2 lines are separating between the input lines. That's okay. So we do need to find the horizontal reflection line. This does not work, so we can basically start fresh. And we do have a function which knows how to transpose the string, which we might use or might not. I haven't decided yet. So let's find the horizontal reflection line that we've got here, or maybe not. By the way, I think we are guaranteed that if we don't have a horizontal one, then we must have a vertical one. I think there will be no patterns in the actual input that have zero reflection lines. So first of all, we've got our rows, and we've got our mirrored. So we've got our two rows. We could hash them because we can like guess that basically each row is going to generate a unique hash. That way we don't need to match up actual strings to strings, we just need to match up numbers. So we could say list map hash, and there we go. We have two lists of hashes, one in a forward direction and one in reverse. Now we've got that. What are we actually planning to do? Let's think about that. So my thoughts were basically, let's hop onto Excalibur. My thoughts were something in the lines of, we've got some sequence. Let's call that 1, 2, 3, 4, 4, 5, and now we've got the reverse of that, but almost not quite. Or I mean, we are not guaranteed it's going to match up, but let's pretend it does, but not completely. So let's do 1, 2, 3, 4, 5, 6. No. How? Okay, so first of all, let's start really simple. We've got that. We say 1, 2, 3, 4, and let's pretend we've got the opposite, which is 4, 3, 2, 1. So in this case, our symmetry line is going to be basically this one. We don't have any matching things except for like one line. Is that a good way to like formalize that? That's not a good way. So how would we want to formalize that? Like we do have basically unique numbers. Oh, sorry, it's something like 1, 2, 3, 4, 3, 2. Or let's call that 4, 4, 3, 2. Yeah, and now we've got like our symmetry line basically. So our symmetry line in this case is going to be on index 4. So yeah, something like that. So this is our symmetry line in this case. So how are we going to figure this, find this place? So firstly, we are not guaranteed that this could also have been like 1, 2, 2, 4, 4, 3, 2, 2, and that is still like the mirror line is still here. So we're not guaranteed that each two lines have like only two lines have exactly the same shape. I think. You know what? Actually, let's actually look at the input, and if we've got that, then that is going to be amazing. Let's look at these inputs. So on the first one, are we going to actually find anything that's exactly the same? Yeah, okay, so first of all, here we've got these two, which obviously are equal. And then we've got also these two, which are obviously equal. Oh, it's different patterns. Okay, so we've got, yeah, these are equal, these are not, these are also. Do we have exactly, if we've got like two pairs and that's it, then it might make our lives very easy, because basically all we need to know is basically we just need to keep track of whether we've seen this hash before. I mean, if it's the previous hash, exactly the previous hash, then we know that we've seen this line exactly just now. That's our symmetry line. Then we can basically stop. So that's actually a very, very easy thing to do. So we could literally just do that. So let's actually add more iter tools. Oh shit, more iter tools. Sync. Will this fail? Please don't fail. I don't have time for you. What the hell? It's failing to install itself. My project tunnel. So we've got dev dependencies. That's not interesting. Tool Rai. Patch metadata. More iter tools. What's going on with that? Let's actually, you know what? I'm gonna do a very interesting thing, which is to say, let's just back this up. Let's call Rai init again. RM PyProject tunnel. Just like that. Rai init. And let's look at the PyProject tunnel that we've got here, which looks kind of the same, kind of like too much the same, I guess. And dependencies are, well, yeah, not interesting. Very much not interesting. If we sync that again, oh, we should probably also add more iter tools. And let's sync once more. And how would this look in terms of like we need a project name basically. Okay, so how does bootstrapping look like? We should have thunder in it, yeah. And maybe we should have like another thing. Not sure. How does a blank project look like? Like the cd hello junk, literally like make cd junk and init. So we should have source, and then in source we should have junk, and then okay, so the name of the module, then something. So let's just do that easy quickly. So we should have AOC underscore 2023. No, shit. That should have been. We should have moved that. So not copy, but move. So AOC the underscore 2023. And yeah, within that, we should have everything that we need. We should also probably have it under init find. But with this now, it doesn't need to be interesting. It just needs to be something. So let's try now cd back into our AOC code. Sync now. If it will install everything, that would make me very happy. Oh, yeah, that's very nice. Okay, so now we should have more iter tools, which is very good. So from more iter tools, import windowed. So now we could literally just walk this windowed thing for every thing. Okay, so we should have row pairs windowed size 2 on grid split. That's very nice. And if we've got that, we return it. Otherwise, we return none. That's very good. And now we've got our transpose, which means that now we've got this thing which also works. Int or none. So now we've got our horizontal and vertical line. And let's try to run that. And we should have our thing. So let's run pytest now. Oh, -k13. Python -m pytest dash k13, which is a thing. It says no module named pytest. Try add dash dash dev pytest. Try sync. Okay, that actually makes us a little bit more yeah, everything now should be a little bit more ordered, and it says module pi has now attribute path. So why is it unhappy with this pi module? I don't know, but let's just move that directly into our pi thing, pi test. And it says has no attribute path. Why should it be? Why should it have that? I don't care about this thing. Module AOC 2023 pi does not have attribute path. Why is it? What the fuck is happening? Which Python is this? Python dash dash version 3.11. And we just installed PyTest. And we are running through the virtual env because we see that we're running through the virtual env. So what the fuck is going on? You know what? Let's open up a new terminal. Yeah, just let's start fresh and run. Okay, so we've got Python -m pytest -k13, and it's still unhappy with us. Get terminal width from pytest compat import final. What the hell? The argument in name Python module without the pipe. Yeah, I did that. Why is it doing that? So we've got PyTest, we've got this thing. Try sync. Sorry. Apparently I need to debug my Python thing. I don't know why. But that's a good thing because I needed to find like rough corners of Rye, so that's good. You know what? Let's actually do the not craziest, but let's remove our virtual env. And let's try sync again. And it will say that it needs to create a new one. And then it will install everything, and then we should run PyTest, and now everything works. Amazing. So was something about the virtual env, and now we don't need to worry about that. So we have 204 and 302. Definitely not what we expect to see. So let's actually test our thing, and we'll figure out what's going on. So we've got our row pairs. By the way, the vertical one, the transpose direction might not be correct, and that might hurt us, but the horizontal one should be okay. So let's look at that again. So we've got row pairs, and each row, by the way, are these, yeah, these are rows, and we do have a fill value. And we are enumerating on this one, which means the first index, oh, so first of all, it should have been +2. Because we always take 2 rows. No, +1, sorry. I'm getting ahead of myself. So yeah, basically +1 because we're always taking the line that's between these. So we're taking this one. That's like our zero index is 1, and our last index is whatever that is, this thing, without any fill value because we don't want to reflect on the last line or something like that. So now that we've got that covered, let's try and run that. And we should see, okay, 305 is still not correct. And why is that? So we've got this thing. Okay, so these are the only two lines that reflect. So how come we're seeing for each grid more than one reflection? So why are we seeing a vertical reflection then? That means our transposing is not like doing its thing. So let's actually test out the transpose. So def test transpose, and this should be grid 1, 2, 3, 4. And we could actually also dedent this. Okay, so we've got our thing, and we have dedented and stripped all of the other things. And a third transpose should be dedent of 1, 3, 2, 4 split. Okay, and now we've got this test, which passes. Let's try 1, 2, 3, 4, 5, 6. And that's it, because we also need to support rectangles. This should be this thing. Yeah. And let's run that. And this is not working. So that's not good. And this is probably a place of pain. So what have we got here? Which is, this is transposing a square basically. And that's because you don't need to, like, don't copilot and drive basically, kids. So we've got backslash. Okay, so how would this need to look? It needs to be rows at place 0, and then that will give us the length of the column, and that's it. Yeah. Yeah, so let's just say call size is length row on this one, if rows, else 0. If no rows, also no columns. That's very good. So now we've got that, we should say this thing. And now that we've got this thing, wait, what? Was never closed. Sorry. Now that we've got this thing covered, let's actually run this test reflection thing. And that is always assert false, which that's okay, but we should have seen 305. No, we should have seen 405, I think. Let's run that backwards, not backwards, but let's look at that. They claim this should have been 405. 405. So as long as this is not 405, we should, by the way, we should assert 100 times h plus v should have been 405. And now we've got these assertions, which aren't working, and that's good. And let's actually test these things. So we just printed our own thing here. So the index, let's look at that very closely. So the 5 thing is working. So the vertical line is working, but the horizontal one isn't. Right? So horizontal one isn't working. It should have been 4 and it says 5. Let's look at that. Wait, but it is 3. So what gives? Or are they not indexing as we expect them to? If you look at that, but they start from 1. What? Wait, what? 1, 2, 3, 4. And this one is... Oh, but these are not actually equal. I see. So it's not only about finding this mirror thing, but we actually should assert that everything is actually equal from that line. So interesting. So that's not good enough. So we don't need to. We basically need to say once we've got that like symmetry point started, we should claim that we should like assert that this like the shortest segment of any of these should be equal. Once we've got that covered, then basically we can claim that we've found a symmetry line. So let's actually do that. So we've got our reflection line, which is just our index. So that's that. So we should say find reflection lines. We can yield this. And for each one of these, now that's going to be basically, we could say this is an iterator of integers. We can return this one. This is now a generator. And now we've got def find reflection line. And that's going to be not next, no. So candidates. These are like our reflection lines, basically. We don't need to list them because we can say for candidate in this thing, if, okay, so first of all, shorter slice, that's going to be the length of, that's going to be the minimum of grid from candidate, and yeah, that not minimum length of this thing and this thing. Okay, so we've got our shorter slice now. And we should say that basically if front be this thing, so that's, wait, let's think about that. So we've got the shorter slice length. So that should be from, so we should have two slices basically, from candidate to short slice, and then okay, so that should be so front, that should be literally slice from candidate to candidate plus short slice. That's one thing, and we should also step that backwards. That's because that's the one, like one of them should be sliced backwards and back. That needs to be let's think about that. No, okay, so that's going to be minus because we don't care about that at this point. That should be forward basically, and the back should be candidate plus, no, not plus short slice. Yeah, so if this thing, then we return our candidate, otherwise we continue forward. So we've got that thing. So that now compares these slices, and then that gives us basically a very well, like a very good thing, basically. We could optimize, and instead of like doing this on strings, we could have like actual ints that represent these strings. But for now, let's just do nothing. Like, by the way, these ints can be literally ones and zeros instead of that. That is a very compact integer. And that's a very unique, that's a completely unique hash for these. These are basically binary numbers. So by the way, these could be like, this could be uber optimized. So that is now 403. No, that's still 305. So let's try to run this with a debugger and actually see what we've got. So not debugger, but let's actually start with just do this. So let's actually print A and B. Let's rerun that. So A and B are these things, and these things. So this is the first one. This is the second one. Ooh, interesting. Wait, but this is an actual reflection line. Like, nobody claimed this is not a reflection line. Like, we could, if we discard this thing, then we've got a proper reflection line. So what? By the way, let's just separate things. Yeah, so these are this is definitely a proper reflection line. I don't see why this is not a reflection line. And this one, if we actually look trace this one, how come we can't actually see it? Oh, because it's the transpose thing. Let's look at the transposition. Where do we have this thing? This is shorter than anything that we've seen. So we've got dot pound something. It's not anything here. So first of all, what? Um, print front back. What are the actual slices? So this is a slice of size 3. So from 0, which is actually correct. This is like the slice. 3 to 0 is this one. Then 3 to 6 is this one. Like 3, 4, 5. Wait, what? I feel like we're losing somehow we're losing rows. Is that correct? No. Wait. Yes, we do. Yes, we are. Why aren't we seeing? Where's this row? Where did it disappear? So this is definitely incorrect. I'm gonna literally print the grid here. Not in the transpose, but actually here. Print grid. I want to see it to make sure to assert that we've got it. Okay, so we've got the full grid. Who's printing the not full grid? So find horizontal. We are now printing it. This is now the first thing that we print. So grid. Okay, so oh, there it is. Damn. That's annoying. Apparently, we should have had something like a new line here because PyTest is not nice to us. in terms of like catching standard out correctly. So we've got our grid. Now we can look at that, and we do see that this is incorrect because this one is not actually a symmetry line. Or is it? No, it is not. It's not a symmetry line because we've got two different things. So what should be the symmetry line in this example? I'm not sure. Back to the first thing. So the symmetry line on the first example should have been this thing. So the vertical one. So we've found our slice. So the shortest one should be basically, if this thing works, then we should say print candidate found. So let's run that. And it says found 3, and that's incorrect because this slice is not actually correct, which means that this is not actually a thing. Because, well, first of all, this is apparently just incorrect. Now it doesn't find that slice. Okay, so 3, 6, and this thing, so hyper, none, and plus. That's very good. We shouldn't expect to find, oh, wait. Yeah, we shouldn't find this thing. So it should say, we should say basically, so result should be 0. Then we should say result plus equals find horizontal line. So 100 times find this. If it's none, damn. So let's just do h equals this thing. Then we should say result plus equals h or and v, but it should be or 0 and or 0. Okay, now we could assert that basically result is 405. Now we've got 0. So now it's not finding anything. So let's find the horizontal line. We do know that we should have found like a horizontal line in the second example. So let's actually look at the assertions that we've got. So we've got this grid, and we found this reflection line. Then we actually we aborted that. So let's maybe print like else. You know what? Let's return 0, and then we don't need to deal with nuns at all. So that's just going to be int thing, and that is now also a thing. Then we don't need to do or 0 in any place. So that should have been a little bit nicer. And this thing, so we got our grid. We say found. Else unmatched. Okay, so we should say unmatched, and that is I mean, we could try to print these things, but probably doesn't really matter. So let's actually see why we got just one thing, and that oh, so interesting. So in this grid, which is the horizontal version, so let's look at this grid again. So we've got our grid. This is like the normal grid. We look at it, we've got basically the same thing. We say 3 is a place of like this might be a candidate, but it's not. Then we should say, oh, another grid. And that is a transposition, if I recall correctly. So let's look at it very closely. We should see the same thing, but just transposed, and it's going to look ugly because this font is not square, it's only rectangular. And then we say unmatched. So why is it unmatched? That's a very interesting thing, because here we do have this thing where we should say the shortest like these shortest slices should match. This slice and this slice are exactly equal. We could actually try and reflect that, but okay, so let's actually print the grid at each of them. So we should actually, instead of like we can print this thing and then basically grid back. And we could also print the slice. We can say now front and then back. And if we run that again, we've got unmatched on something that's definitely incorrect, which is interesting. So these things are not actually the slices that I thought they were. So this grid, okay, but we do see the grid, which means that grid at front and grid at back is not the thing that we expect it to be. So printing the two slices, this is basically, this should have been, wait, why is it slice none? Okay, so you know what? Let's actually do the slices in place. So we should say, okay, so let's think about that. We should have from the candidate to the shortest slice length, and from the candidate back to the shortest like. Okay, so we should say candidate minus shorter slice length to candidate. That's 1. So these are the front things, and then we should say from this thing we should take this, flip it. These mirror images should be okay. So, and that should have been candidate plus step -1. Yeah, I think that should be it. So let's just try to print them out. So we don't have any more front and back. Let's actually just print these symmetry lines, and then it will fail directly on that because I basically just didn't define things correctly, and it still prints weird things. So we should see, where's the dash 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 thing? So this one is printing A and B, which are the row pairs. So we don't need these anymore. This is like kind of working, I think. So yeah, I think that's good. Oh, we could literally just start with 1. Yield I. Yeah, I think that's nicer. That means that we don't need to do any like arithmetic every time. That's quite nice. And then let's actually, yeah, let's extract that into a variable. So that's going to be front. That's going to be back. And then we can say if front equals back, then we're happy. And then it says unmatched on things, which makes me sad. So let's just first of all, let's actually print. So that's going to be pair. So we've got pair, unmatched on 3, and then it's printing an empty list. So the back one is not actually printing anything, which means that this slice is not doing what we expect it to. So that's going to be, let's actually look at that more closely. So we do have our index, and we do want to split it exactly in the middle. So up to some index, and from that index onward is actually the right split. I think. And we do, oh, we actually see that this is the slice. This is the found candidate and unmatched candidate. Okay, so let's look at that. So why is this not doing the thing? This is grid. Is grid a string, or is it all rows? Oh, it's not the lines. Interesting. So these are just strings. It should have been a list of strings. So yeah, this is split into lines. So let's just have that as a list of lines. Apparently, if I just would have coded things correctly, it would have been maybe correct. But if I coded incorrect things, that is not going to be correct. So yeah, lines. Split. That's very good. This one is just now probably going to be a little bit better because we're not going to like print short slices. So yeah, there is nothing as grid. Does not exist. So we've got pairs, and now we've got actual things. Interesting. And the second thing is always 0 width, which means that this is not correct yet. So we should. Interesting. So candidate to the shorter slice length. Let's look at that. Why is that not working? Let's just try that in our Python console, and then if that won't work, then okay, so Python console. So list 1, 2, 3, 4, 5. That's going to be L. Then we should say, first of all, we have access to L. Great. So how do I, and let's just call that, now we've got some I, which is, let's call that index 2. And I claim that I want, and S, that's going to be also size 2. So I want a slice of size S in both sizes. So first of all, L at S, and then, not S, sorry, L at I through I plus S. That's going to be 3, 4. That's very expected. And then if we stride that backwards, interesting. And if we actually flip these around and we say I plus S through I, stepping that backwards. Sorry, stepping that backwards. And that is going to be I minus S. What? Wait, what? So this is actually stepping things backwards, but it is doing that from what? Um, I'm very much confused. So yeah, this thing is apparently not how to write this. So how would I write this? So I want basically, let's try like the craziest thing, which is the same thing, but with a negative stride. Okay, yeah, shouldn't have worked and doesn't work. And then let's actually look at that a little bit more deeper. So we've got our lines, we've got a list of things. Back to the console. So console. Python console. So how would they index into things? Apparently, I don't know how to do reverse iteration in Python. So let's just do Python reverse iteration. Um, so reverse slice. That's actually so we should say we should keep the bigger index on the left side. Wait, what? Okay, so first element to include, first element to exclude, step. Um, so first element to include is going to be the candidate still. And the first element to exclude is going to be candidate plus thing. But that still won't work because we'd want to actually, okay, so that is actually going to be candidate plus one. That's going to be the first one to exclude. And that needs to be this. This is going to give us an actual list. No, this is actually still too short. So -1, and that is still too short. Um, so the shoulder slice length is always the same. I've got like a very crude thing that I can do, of course, which is to say candidate through candidate plus the shoulder slice length, not do the reverse iteration here, and then we can just reverse that in one more go. And that is now working. Wow. Okay. So I'm not sure what do I need to do in order to make things work, but this is good enough for now. Okay, so we've got that, and it might be the other one might be this thing, and we could try and run that into a like onto our actual input, which is a bit large, but sure. So we've got define. Let's actually just let's call that part one. So part one needs to take some input, stir and return this loop. So yeah, we should say this thing. And we can return that. We can, of course, try to parallelize that, but let's try not to. And then we could actually assert that, let's test part one. That would conclude this part is part one on part one equal text, and that should have been 405. And it says part one expects a string and, oh, sorry, list of stuff. Yeah, okay, so our assertions are working. We can try to, okay, we can try to comment things out. So yeah, we can remove all of these prints. We don't need them anymore. Oh, and we don't need this. Okay, so our tests are passing. Let's actually have like our input day 11, whatever, day 13, whatever that this thing is. So inputs, D13, delete everything, copy the thing from this thing, and okay, So now that we've got all of that, we could actually try to run that on the thing, which is if under name equals main. We could actually open this a little bit more. So this is the tests, and then it should have been inputs day 13, d13.txt as f, read blah blah, print the thing. And run that. Python tests day 13, and it says no such file or directory. Okay, so we got a number. And is it the correct number though? We'll figure it out in a minute. Okay, one gold star. Continuing onwards. You resume walking through the Valley of Mirrors and smack run directly into one. Hopefully nobody's watching because that must have been pretty embarrassing. Upon closer inspection, you discover that every mirror has exactly one smudge, exactly one dot or pound that should have been the opposite type. In each pattern, you'll need to locate and fix the smudge that causes a different reflection line to be valid. The old reflection line won't necessarily continue being valid after the smudge is fixed. Here's the above example again. The first pattern smudge is in the top left corner. Yeah, and once we clean that up, then we've got a better reflection. Instead of that, it would have a different horizontal reflection line. Yeah. With the smudge in the top left corner repaired, a new horizontal line of the reflection between rows and 3 and 4 exists. Row 7 has no corresponding reflected row and can be ignored. But every other row matches exactly row 1. Matches exactly. Okay, so yeah, we've got like basically a new symmetry line. Okay, so how do we know where the smudge is? Okay, so yeah, the second one is now this is the one. Oh, wait. With the smudge on the top left corner repelled, yeah, okay. In the second one, the smudge can be fixed by changing the 5th symbol on row 2 from dot to pound. So the new pattern has a different horizontal line of reflection between rows 1 and 2. To summarize your notes before, but instead use the new different reflection lines. This example, the first pattern's new horizontal line. Okay, fix the smudge. Okay, so how are we going to fix the smudges? So in each the example, the first pattern's new horizontal line has 3 rows above it, and the second pattern. Okay, summarizing it. But how would we know where the smudge is? Okay, so the smudge can be fixed by changing the 5th symbol on row thing. In each pattern, you'll need to locate and fix the smudge that causes a different reflection line to be valid. The old reflection line won't necessarily continue being valid after the smudge is fixed. Here's the above example again. The first pattern smudge is on the top left corner. Okay, if the top left were instead, okay, so with the smudge in the top left corner repelled, a new horizontal line of reflection between blah 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 has, okay. In the second pattern, the smudge can be fixed by changing the 5th symbol on row 2 from dot to pound. Um, Now the pattern has a different horizontal line of reflection between rows 1 and 2. Summarize your notes as before, but instead use the new reflection line. In this example, the first pattern's new horizontal line has rows blah 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 blah. But what number do you get after summarizing? But which one? How do I know where's the smudge? I mean, how do I know which bit to flip? This is a very interesting thing, and I'm gonna actually open up the hints of like other people because I'm impatient. Um, so yeah, this is going to take a while, like to actually open up. Let's try to reread that again while I'm feeling definitely less intelligent than any other day. But yeah, okay. So where the fuck? How do we know where the smudge is? We have no algorithm for that as far. Um, every mirror has exactly one smudge. Um, in each pattern, you'll need to locate and fix the smudge that causes a different reflection line to be valid. So is there exactly okay? So interesting. So there's one thing, one uh one coordinate that you can flip and will change the reflection line. And all other things won't do that, won't let you actually won't create a new reflection line. That is not correct because okay, so every row that has like a freestanding column, or like every reflection line that has like a freestanding set of rows and columns doesn't really matter because this will not actually change the reflection line. So we need to flip the only bit that actually moves the reflection line. And there's exactly one. So obviously, we should do like some kind of caching because this would take a while, right? Or will it? So, um, let's think about that. Um, okay, so let's think about that. Let's literally do. Okay, so I'm gonna first do it like inefficiently, and if it's actually going to take some time, then we are going to um, do the thing where we actually try to optimize. So part two. How does part two look like? We need to fix the smudge that changes the reflection line. So how would we do that? So first of all, we do have this thing, which basically is its own thing. So we could say, we could have the extract that into a function, which is to say, um, um, find reflection. So this thing, which does return the tuple of thing and thing, we can cache that. We can, of course, cache this thing. And we can, of course, cache this thing as well. So everything should have a cache. But apart from having the cache, we are in the trouble where we actually feed different things into like the grid changes by a lot. So how do we know that we haven't done the thing? We need to like have another layer of caching, basically. And that layer of caching is somewhere in this algorithm. Um, So these things actually, if we got to this area, wait, find horizontal thing. So how would we cache all of these reflection lines? Okay, so we can actually, okay, so def. So instead of doing that like directly, we could say inner. So let's call that possible reflection lines. That's an iterator, and that's going to be this thing. And here we can return the list of possible lines that can be cached. And that gives us, that's going to be a list now. Awesome. So this one is now caching. We don't need to do any like computation here. We should have like the same list basically for each kind of like each set of lines. We should have that. That might blow up like memory because we are doing like a lot of things. Is that maybe a good idea to have now? Let's try to maybe convert that into numbers. Interesting. If we'd have that as a sequence of numbers, that might actually be a little bit more compact and fast. So let's do that. Let's call that T, and T is now stir. Let's return T, E. And these are integers because these are indices. So we've got this thing, and this is no longer valid because this is a list of, this only works with strings. So we need to think about that a little bit more. So we've got this, and yeah, okay, so all our spaces and joiners are actually like string oriented, so that's not very good. So let's actually do this where we say, yeah, let's add these as a hash. Okay, so interesting. That is actually going to be a not string to string, but that's, or maybe this needs to be string to string because that's our transposition. Okay, so this is the thing, and then here, let's actually convert that into like the more compact thing, which is, okay, so def compact. So this is going to be some s of type stir, and that is going to return a list of integers. So return hash on s. Or s and s. Oh shit. So these are like, that's the full grid. And we do want to have this as a line, so hash for line and grid split. And that's good. Compact cache. Okay, so we've got that. And now we are able to say compact on transposed. And this thing also needs to be able to accept compact things. We could compact this well. And we do have, this no longer is, this is a list of ints. So if we've got a list of ints, this is already lines. We don't need to like do this anymore. Lines. And this one also accepts a list of not strs, but ints at this point. So shadows, lines from out of scope, that's okay. We can underscore that and underscore that. And horizontal, that is not going to work. We need to compact line, right? No, wait, what? That accepts a list of ints, and that we are passing a list of ints, right? Int. Okay, no t's for us. lines to list of lines. Wait. Is that a different kind of thing? No, that's actually that is correct. Expected hashable got list. Ooh. Tuple. Tuple, 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 tuple. Yeah, we need a lot of tuples basically. Um, so this is now a tuple. And for things to become tuples, we need to do some work. We could also, like, instead of like hashing each string, we could literally convert that into like an actual binary number, which is even more compact. Oh, I see some people joined. Hi. Yeah, now part two is actually not working because it's unhashable yet at this point, so compact should have become, well, a tuple of this thing. And that is going to be a tuple as well. And our tests are back to passing, and now we've got, let's actually run that on the thing, the big thing. Yeah, okay, so we got the same answer, but now we've got like hopefully better performance because we don't need to do string comparison. All we need to do is actually compare bits, like numbers, integers. So now that we've got that, oh, let's actually use find reflection also here. So that would also give us a little bit more confidence. So part one is now working. Interesting. So find reflection on grid. So this is broken. Interesting. So let's look at that. So find reflection on grid is actually going to be, yeah, we're going to find these candidates. Print front back. Let's actually look at these. So why are we having actual like strings forwarded here? Interesting. That's not good. So this should have been compact. So find reflection. Oh, I see. So this one is actually, okay, so for the horizontal, we have to compact this. And for the other one, we don't, because this needs to compact it inside. Okay, and now we've got our tests back to passing and our numbers are looking okay. That is running part one. Yeah, that's running part one on the input. Part one is now finding the reflection and everything's fine and everyone's happy. So now that we've got that, let's actually try to find the thing, which is, so we need to say for each, we need to keep track of like, first of all, like literally run part one as part of our thing. So we should say, for in part two, we should say, HV pairs are going to be a dictionary. That is going to be basically, yeah, so HV pairs. Oh, sorry. HV pairs is going to be grid to HV. Okay. And now that we've got our cache, basically, so we've got our like for each grid, we do know what is the actual part one thing. Now we should say for so we need to mutate the grid now for each bit and then actually try again. So how would we do that without like causing total mess in our memory? We don't need to do this anymore, not at this point. So we should say for grid in thing, and then for um, flip one char in grid, find reflection. If oh, so we should say our key basically is if we for the same grid and we get the same HV, then okay. So if HV pairs at grid equals HV, then we need to mark interesting. So okay, first of all, if H plus V equals 0, then we don't need to do anything. We should just continue. And we could have been like a little bit more, let's call that like a little bit more clean with that. Okay, you know what? Yeah, okay. I think that's good enough. So for flip one char, or flip every char. Okay. So flip one char every time. We should have, yeah, find reflection. Are we actually doing any caching like at any point like over an actual like one line? Probably not, right? That's not good. Yeah, we're not gonna find a lot of things to worry about. We're not gonna have a lot of caching opportunities here. So if this is actually the thing that we don't need to do anything, if it's exactly equal, then as well we don't need to continue. Otherwise, we can break this grid. Can break out of like flipping the chars. Okay, so let's actually implement flip chars. So how would that look like? So def flip chars. So this is going to be an iterator of strings. That's actually correct. And then we should say this thing. If it's this char, then we say this. Otherwise, yield grid. No, we just continue on. We don't yield like grids that aren't multiplied. So yeah, I think that, I mean, this is a very like the most inefficient way to do this. Is there a way for us to actually have that in Python? Yes, but only if we actually change things into not strings, because strings are immutable in Python. So how would we want to do that? We could have literally an array of bools, and then everything we can do is going to work on booleans instead of strings. But that means we lose some of our compactness. So are we going to do that? Let's think about that. So basically, I just want okay, you know what? Let's actually, if this actually takes a while, then wait, top level collect. Why is it unhappy? Because we've got some thing that isn't like not a thing, basically. So first of all, flip chars. So for something in flip chars, sorry. So for for option in flip chars, then find reflection in this option. And if this is, yeah, this HV is with the same key with the grid, then we are okay. And since hashing strings is not as fast as taking their memory address, and we do know that these are unique in their memory, so we could actually say this. It's the same memory address, I think, because we are iterating over the same list of objects. Usually that won't work, but in this very specific case, it could. And then we should say, instead of breaking, we should actually say HV pairs in grid is this thing. So if we've got 0, that means that we have found no reflections. If we've got not 0, but anything that's exactly equal, then we don't need to do anything. If we've got something new, that means we found a new reflection line, and that should give us thing. And then we should say sum over. Oh, we could also have like a copy, so that's going to be our reference. So HV pairs. Okay, so that's going to be not HV pairs, but previous. That's going to be HV pairs dot copy, which would give us like something to check against. Now we could say assert for KV in HV pairs prev key. No, they all should be different. So if we could literally assert prev key is not equal to this thing, and then we could sum on the HV pairs. Yeah. And that is now not doing anything fancy. We could now add test part 2. So how would part 2 work at this point? We do have the same input. So for the previous input, we should now have a value of 100, 400. So that is not going to pass, and that's because 405. Oh, wait, what? Part 2, HV pairs. Okay, first of all, print HV pairs. Let's actually print them. So we've got where's our thing? And that is definitely not good. ID grid, find reflections. Grid. Where part 2 is this call? How come we haven't seen this print? Part 2 is actually, let's run that only. Captured SD out call. So we got 0405. Interesting. So let's look at that. We should actually look at the flip 1-bit thing, which should have actually taken a while, and I'm surprised it didn't take a while. So we've got our list of inputs for option in flip charts. So let's actually print that. That should spam the hell out of our thing. And it does not spam. This actually is quite mellow. So for flip charts in grid, let's look at that. So we've got our enumerate thing. Grid string to thing, and then it says yield grid up to and from to. First of all, let's actually add a little bit more prints here, which is let's do option Okay, so we've got not a lot of grids, which is interesting. So flip charts, that's giving us a grid. Why is this not yielding like a bunch of grids? Would expect this would like spam our computer. So if char, is this actually a thing? Is this, so part 2 is receiving the text as it is as a list of strings. That's a list of strings. And for each grid, got print, grid, grid. So we've got our grid. Then we flipped this bit. Interesting. So first of all, we should have flipped this bit. Oh, and then we're done. Are we done though? So this should have returned. Let's look at the actual reference. This should have returned. So with the smudge on the top left corner repaired, the new horizontal line should have been between rows 3 and 4. Now it should have been row 7. No, has no corresponding reflected row, but everything else matches. Okay. The second pattern, the smudge fixed on the 5th symbol. Wait, so did we fix actually? So let's actually print not only this thing, but actually, how many options have we iterated through? So let's iterate, flip grid, flip chars, and that's going to be I. So option I. So we should see like option 0 and then 0, 1, 2, 3, 4. Interesting. So that's actually correct. That symbol flipped is actually the thing. But we might have wrong logic somewhere else. So if h plus v is 0, oh, we could actually just do h times 100 plus v. Not think about that anymore. And then that is just r. And then we don't need to think about it. Oh, but we do want HV plus because we want to compare against them. Like we want to see that they both changed. So that needs to be like H and V. So we've got H and V. If they both sum up to 0, that means that we are fucked. Not fucked, but basically we don't have any new reflections. Not like this thing is not reflectable. If ID of the grid, by the way, grid ID, let's have it here. Would this be maybe a different thing because it's an iterator? No, because it's a list of objects basically. Input is a list of objects. So and we're also not throwing any key errors, so that's probably okay. So let's think about that. So if their sum is 0, then we don't do anything. If it's the same, then we continue on to the next iteration. Basically meaning it's right after the 100% line above the red. Oh, doesn't process the second onwards. I have no idea when did you write these lines. Like, Ran. Thank you for joining, by the way. This is a very exciting day. Like 100 videos is like no joke for me, at least. So let's actually do that. The grid print on the same line. Glad to be here. Thanks. So yeah, the things are being printed. Okay, you know what? Print. Yeah. Now we got it. So basically this is we can print the previous one and the new one. So we've got our HV pairs, and we also want to print our new HV pairs. So they should be different, and they are on both things. But the fact that we've got 3 and 5, that's crazy. That's like not the actual thing, right? Probably. So why is it reflecting on both 3 and 5? So let's actually flip the let's stare at this pattern closely. If we flip this one, so we've got row 3, and we've got this thing, which is definitely a reflection. So these 3 rows and these 3 rows are reflections. But also, the first one isn't gone. Like this line, this line, let's look at it. So we've got, yeah, it looks the same. Are we guaranteed to not have like dual reflection lines? I don't think so. Should it be H or V? I mean, kind of sucks. Let's look at. So it must cause a different reflection line to be valid, and the all line won't necessarily. Okay, so it can continue to be valid. But if we flip this thing, so summarize your notes, but instead use the new reflection lines. Interesting. So the first thing, okay, so we should ignore the previous reflection lines. So that actually means that we need to have H and V as different things. So so we've got H and V as 2 different dictionaries, and then we should have H at ID grid, and that's H. Ah, crap. So that's going to be H's and V's. H's and V's. And we do want grid ID as a thing. Grid ID. And now we've got H's and V's. And then we should say rev H's. That needs to be hs.copy, rev V's as thing, and then we should have this the same thing where we say if any of them match. Okay, so this is the point where we need to basically either filter or change stuff. So let's think about that. I really don't like this so much. Like, this is kind of not good. In the previous one, not even sure if we had like duplicate lines where we had like this like 4-way symmetry. Now we do have that. But we've got fine reflection. And we found the H and V on this permutation, let's call it permutation. It's not a permutation, it's a mutation. So for each thing that we flipped a character, then we've got that. If it sums to 0, then like this is not a valid thing because we don't have no h's nor v's. If h is at grid ID, comma v at grid ID is equal to this thing. So if we've got like this tuple equality, then we know we haven't actually modified anything. And that means that we can like skip this. So this bit flip is not relevant. But if it is different in some sense and it's not zeros, then we do want to store that. And how would we want to store that? We should say yeah, we do want h's and v's to store that differently, separately. And now we've got h's, v's again. And for each of the zip of h's and keys values, oh, there are no interesting. So this insertion is actually not correct because we might have these. So how are we actually going to do that? We'd want to say only, okay, so new h's is going to be, well, a dictionary of different than, and new v's, same thing. Then we should say we just want to sum the values basically. So we just want to zip the values. And now we've got like something, and the something is 0, which is definitely not what we expected to be. So for any ID, we've got like the 0 and 5 now split, which is very interesting. Also, the char flipping logic stops after the first line, I think. No, that's not correct. So as you can see, it does continue flipping, and we're going char by char. We're not splitting by line. It's basically the contiguous string. And if we reach a new line, then we just don't yield any new permutation. That's it. So at the flipping chars thing, we can actually like assert how it looks, but you know what? Let's actually do that. Because unit testing is nice. So def test flip chars, and we do want to say grid. No, we don't need all of that. Oh, that's definitely. Oh, Copilot, you're ruining me. So we do have. Let's just have thing, new line, thing. And then we should say that we should have 4 permutations, and these permutations should be this thing flipped, and everything else is okay. Then we should have this thing flipped, and everything's okay. Then we should have back to normal here. This is now flipped, then this is now flipped, and this should have returned into being this. I think let's actually run this test specifically. And we've got 4 things which are a little bit different, and we should just, okay, so first of all, we didn't stop after the new line, and I do have probably a bug somewhere. So where's the bug? Where's the bug? So first of all, this is just incorrect. Let's run that again. By the way, are we actually running the original permutation? The original permutation doesn't really matter because we are running against a cache that saved that permutation because it's the golden one. But basically, okay, so first of all, first thing, this is the same. This is the same. This is the same. And this one isn't because I fucked up. That should have been dot pound. Okay, so our bit flipping logic is working. We could have done that like a little bit more efficiently, but for now, let's just use like this is going to allocate a lot of junk on the heap. But good thing in our that like we've got in our, under our hands, which is like Python is really good at allocating a lot of small objects. So hopefully that's going to be okay. So back to actually the debugging the thing. So we've got our thing, which is we are going to we are adding all of these pairs up into our H's and V's. The only reason to save them separately is basically to make sure that we don't count the things that are not new. Because this is what they said. They said, summarize the new reflection line in each pattern in your notes. So the new reflection line means that we've got something that's novel. And how would we actually know if something is novel? Because we kept a copy around and we know like what is actually new. So new h's is going to be grid ID. Oh, we can actually can have that as a list comprehension. We don't need the key. So for each grid ID and h in the new h's, if it's different than the previous one, then we want it. So let's do that. Let's print new h's and new v's, and let's run them over, and we should see something. Let's test part 2. So let's look at that. So this is a list of everything wrong and everything wrong, which is not good. So we should have seen 400. How to reach 400? Wait, summarize your notes. The first pattern's new horizontal line has 3 rows above it, and the second pattern has a new horizontal line 1 row above it, summarizing the values to 400. So we should see 1 and 3. But, oh, so we do see 1 and 3. Oh, interesting. So why is that not summing up to 400? Are we doing like a wrong arithmetic thing? What's the actual assertion that we've got? Attributor. Shit. So new H's and new V's. And is it wait, they might not be even the same length. So literally we should sum on okay, so we could literally sum on directly on that. So we could say 100 times this thing, and we should just say sum of new H's and sum of new V's. Woo! And now it's running and actually working. Let's run that over the actual thing where we say print part 2. Let's run that through our console. Okay, that was very quick. Like surprisingly quick. And it's too low. Shit. Okay. So okay. The whole option thing is spamming our way our thing. So how would we want to actually only sum the things that are new? So we've got our new H's, new V's. Let's run that. Okay, how would we know what's what? Option. Okay, so this is quite big, which is kind of hard to debug. How would we know how to debug that easily? So we've got these things, which are just the multiplications, which are, it's quite annoying because I want to actually look at the raw numbers and not the thing. So we could go back and say h's and then just multiply h's by 100. So that's going to be 100 times h for h and h's. Okay, so now that we've got that, let's also run that through against our previous p's. So we could say print rev p's and maybe as a list and like dot values. And we could also print that as well here. What are we missing? Parentheses. Okay, so wait, but that won't help us because that is still not good enough, I think. Wait, we've got like a completely different number. How is that happening? I thought I didn't change anything. So what? Sum of h's. I'm gonna submit that just because it's here, but I don't believe this is a true answer. Too high. Yeah. This number is not cannot be correct. And then we should have said, yeah, first of all, this should have been new h's. And now everything should have been should like go back to being some kind of number, which is still incorrect, but at least we don't have that bug. So what else do we have here to debug? So I'm obviously suspecting this thing. Like this is the like the business logic. So the flipping chars is sort of working, or at least I claim it to be working. If the sum is 0, then I stop that. But you know what? Would that count as, I mean, it would count as not equal to the thing, but it does save us like a little bit of access, like memory access instead of like we don't need to hash things. By the way, I'm noticing this is kind of like actually quick. This is not taking a long time to actually flip the bits, which also is a little bit surprising. I wouldn't expect that to be so quick, but apparently it is. So if they both are equal, then we continue. If neither of them, like if any of them is like not equal, then we don't continue and we actually save this thing into our new thing. Do we want to maybe not copy? Would this change anything? Would this do any actual like? Would this make a difference? I don't think it would. So we got our H's and we got our V's. We've got our previous ones. These are items. We are going to K values. That's okay. Bum, 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 bum. So for each of these, We are only taking the ones that are different. Let's look again at the instructions and make sure that we're not doing anything. Wait, summarizing the new reflection line in each pattern. But should we still multiply by 100? Yeah, summarizing is like the function called summarize, basically. Okay, so we should still have that. Yeah, we also have a value of 400, which means that it's definitely multiplied by 400, by 100. So what number do you get after summarizing the new reflection line in each pattern of your notes? So the new line must be not the old one. Which means that we want to start with an empty dictionary. That's good enough. We just don't need the old ones. So sorry, the other way around. The other way around. This is just our H's, our V's, then H's is a new thing and V's is a new thing. So we just rename them. Or we could literally, don't care about that. Okay, yeah, separation of things, of the things that we do. So this is basically just part one. We just do like a little bit more memorization of these things. And then once we've got that, so if it's zeros, then we don't have a new line. That's okay. If we've got something that's equal to the thing that we haven't changed anything, that means that we don't get a new reflection line. And if we do have a reflection line that's different and it's not zeros, then we've got something. So in this case, we would like to save that. We might find that we've got two values which are actually valid reflection lines. And in this case, we would like to filter these out. So I'm confused. I think this is actually correct. Like I'm quite certain this is actually doing the thing that it's supposed to do, which is not good. HS.grid IDs. Wait, what? HS. Prev. Pam. Yeah, shouldn't change anything significant. We've got our two sets, which are very, very not very like not very big. So we could actually try to maybe do that. Okay, we could also like maybe for debugging purposes, we could say like which bit did we flip? But I'm not sure if that's actually interesting. Hmm. Um, I don't have any ideas. I don't have any ideas, and I'm kind of tired. So, cheating. We've got that right. We've got. What happens if we remove this? I mean, it shouldn't matter. Shouldn't change anything. Why did it change? Wait, what? Why if h plus v is 0, it changes the thing? Um, so this is continuing. This is what? Wait, it's all zeros? What's going on here? Oh, because it's different and it's all zeros. Okay. So yeah, we must skip that basically. we must skip all zeros because everything changes to all zeros basically. Okay, so we must protect against all zeros. Do we need to protect against partial zeros? Let's think about that. No, it's okay that we'd have one component which is zero and the other component which is valid, which is the thing that we actually aim for. But we actually could say, let's think about that. So it's not all zeros. Then we could say um, I truly do not know. What happens if I don't do this filtering and I just say H's and V's, basically? So H's dot values and V's dot values. Then we get 405, which is not the thing in the tests. That's why we did that. We had to filter that out because that is actually how we passed our unit tests. So this thing actually passes the unit tests. And then something else is like our unit tests are not covering the behavior that the other thing does. So let's see if we've got like a very small input. All of these are quite large, right? Yeah, quite large. Interesting. Do we have like a very good way to find the bit flips within our like these inputs? Probably not, right? This is like quite terrible. Yeah, staring at this probably wouldn't help. Okay, so first of all, like, okay, we can take this one as an example, an interesting example. So here the symmetry line is line 3, but then if we flip this bit, then we've got a new symmetry line over this thing as well, over this line. And that should invalidate the first one because we shouldn't use the first one if we found like this bit flip. So and that means we don't want to use the first iteration basically. Okay, so we don't want to use this one at all. So how would we do that? First of all, let's do one assertion, which is let's just assert that for all of these, all of the like actual values, h equals 0 or v equals 0 for zip values of these. This, by the way, all of this like iterations over dictionaries is only like valid in Python, which is an because Python has like all the dictionaries. But this is definitely not like a thing that you can assume on any like other language that has hash maps. So we've got that covered, which means that yeah, like everything here is exactly what we expected. It's either V or H, but never both. So this one is an actual like we've got some like behavior covered. That's very good. But that also means that we can invalidate only on one of them. We don't need to do like the whole tuple comparison thing. So we could take only the other value. Let's think about that. Hmm. I am this H versus H, V versus V. Okay. Okay, let's try that again. Okay, so if H is not 0 and H equals to the previous one, then this thing. Otherwise, if this is the thing, so this might be a little bit better. Let's actually test that out, and we've got to 100. Interesting. So that's not good. So why is this not working? This I would expect would be equivalent. And that might be the root cause, or like a signal that I have missed, like a very important thing. So for each permutation that we did, we get if H is not 0 and it is the same as the previous one, then we continue because we haven't updated it and it's no. So we must look at the tuple, right? Because we do want to actually test both. So if this is the thing and this is the thing, and V is 0. H is 0. Okay, so this is now back to the same place. And we got the same number. Crap. Um, so for each grid ID, um, I just want to see like how far are we like getting into the thing. So let's try add TM rising. I'm glad I didn't choose Rustful today because I'm very running low on gas. Why is it not updating? From TQDM import TQDM. Uh, not the thing that I want to run. That's the thing. Okay. Okay, so we're running quite a lot of like bit flips. Like some of them are like a lot of bit flips. We could also assert an interesting thing. That's actually a good, I mean, an interesting assertion. So we can assert that for each of these eyes, like we could literally assert I is not the length of the grid. No mutation found. And like let's pretend that I is always there. Yeah, okay. So we have never reached the end of the grid. We always found like some kind of permutation, some mutation that actually worked. So that is not a problem. So what is? Yeah, so sometimes we like the first bit flip. We could actually, okay, let's actually run that with PyTest. Value error. Too many values to unpack. Oh, yeah, because I removed the enumerate thing. So let's actually run PyTest like so. PyTest -s. Is it not -s? Like I want capture. Never mind. Okay, yeah, that didn't work. I want like the TQDM to maybe print out. No, I'm wasting time on the wrong things. Yeah, I got nothing. Truly nothing. Yeah, cheating it is. I'm tired. Um, Day 13. Let's look at that. So we've got, they found the reflection index, which they do by doing something. That's okay. Score, pot, D. Map, score, node 1. So score. Allow mismatches. Well, that's a very interesting way to say that. Interesting. So must be exactly the difference of one. Respect. Respect. Wow. That's like a very, very nice way to claim that. Interesting. So are we going to try and build that ourselves? We could. And then that's going to basically, yeah, so it's going to be exactly one mismatch. That's very nice. Like I very much appreciate that. Like this is a very nice solution. I'm impressed. So do I want to actually do that? I think no. I think I want to admire the fact that someone is smarter than me. This is the solution, and I will not copy and submit that. That's actually just very nice. So this is like good software engineering, and that's not mine. And I truly appreciate like this thing. Um, and now you do too. So with that, I bid everyone good night. And think about things in terms of differences and not by like strict equality. And things might be nicer for you. And yeah, been a nice 100 days. I will try to like finish up Advent of Code at some point. I might like have more time for that in the weekend. Like usually during work days, it's kind of difficult to like um, invest a lot of focus in that. And yeah, see you tomorrow then. Bye for now.